And the title of my presentation is a surface conductance-based fully integrated CMOS humidity sensor without post-processing. Here is the outline of my presentation. And as there is a growing interest in IoT, a smart sensor which makes the essential component of an IoT are being actively researched. And processors, memories, and transceivers are three main building blocks of an IoT smart sensors, and they are already integrated in CMOS. However, unlike these building blocks, sensors which convert a physical signal into an electrical signal is not yet fully integrated in CMOS. Humidity sensor especially lacks in CMOS integration compared to other environmental sensors. For this reason, our research focused on the CMOS integration of a humidity sensor with small area and low power consumption. And I will briefly tell you why humidity sensors have not been fully integrated in CMOS. As a widely used figure, relative humidity can be represented in this equation. And as you already know, humidity is not an electrical signal and it does not change the property of the CMOS process. Therefore, previous work and commercial humidity sensors have required additional post-processing, which relates relative humidity and electrical signal. The material that they used for post-processing can be seen here, and this material causes additional cost during the CMOS process. Therefore, to fully utilize the advantage of CMOS, manufacturing a humidity sensor without a post-processing is substantial. And this is the motivation of our research. And the humidity sensing mechanism that we propose in this work is shown in the figure. Unlike the conventional method which uses additional material like sensing film, our research uses a SiO2 surface as a transducer for humidity to electrical conversion. As the SiO2 is provided in any CMOS process, our proposed humidity sensor can be manufactured without post-processing. And I will briefly introduce the sensing mechanism of our proposed sensor, the surface conductance. Surface conductance refers to the degree of current flowing between two electrodes on the surface of an insulator. Then a water drop on the insulator, like this, will act as a conductor. It provides a moving path of an electron, allowing hopping. So, if this voltage is applied to two electrodes, then current will flow through the surface of an SiO2. And the surface conductance has an exponential relationship with the relative humidity. So, if the constant voltage is applied to the two electrodes, then current will increase if the relative humidity increases. Using this property, we can implement the surface resistor. The surface resistor using surface conductance is produced by such a manner. And we use the top metal of the fabricated chip as two electrodes and measure the relative humidity by measuring the surface conductance of SiO2. We chose a combo structure for a surface resistor to minimize the size of the chip. And the surface resistor can be equated using this equation. And as you can see in this equation, the surface resistor is only a function of the relative humidity, because the alpha and the C in this equation is a constant in the fabricated chip. this figure shows the structure of our proposed humidity sensor. The sensor consists of a surface resistor and a load converter. If the constant voltage is applied to the surface resistor, this point and this point, and a certain amount of current will flow through the surface resistor, depending on the relative humidity level. And as I already said, the current flowing through the surface resistor has exponential relationship with relative humidity. So we added a load converter to linearize the signal. And this load converter is composed of an op-amp with a diode feedback. And as this diode has as the current flowing through this diode has exponential relationship with the bias voltage, the output voltage will be linearized. Finally, the output data is collected using the lab view. The proposed sensor was fabricated using 0.25 micrometer CMOS process, and the left figure shows the diphoto of the proposed humidity sensor, and the right figure shows the SEM photo that shows the surface resistor. And we cannot see the circuit of the load converter because the load converter is placed beneath the metal. The size of the fabricated chip is 0.72 millimeter by 0.7 millimeter. Now I'd like to show measurement results of the proposed humidity sensor. The proposed humidity sensor, total 8 chips were tested over the relative humidity range of 30% to the 100% RH, and the x-axis was measured using the commercial humidity sensor. And the left figure shows that the output voltage is decreased as the relative humidity increases due to the increases of a current flowing through the surface resistor. And the right figure shows the measurement error of the fabricated chip. And the chip-to-chip error was measured to be less than plus minus 2% RH. And we also tested about the temperature effect. And the result shows that the effect of temperature variation was measured over 3 different temperatures, and the result shows that the gain error is small with the slope of the result, and while the offset error is large. And this effect is mainly due to the temperature dependency of the diode in the op-amp feedback. Here is the comparison table with other previous work and commercial humidity sensors. And it shows that the power consumption is very low compared with other previous work, and this work only does not use the post-processing. And also chip-to-chip error is very low compared with other previous work. And to conclude, we proposed a CMOS humidity sensor without post-processing the first time. Having a small form factor, it only consumes 4.5 microwatt, and it shows a good chip-to-chip accuracy. And for the future work, we are planning to add a compartment that compensates temperature compensation. And also, we expected that we can reduce the chip size further if the size of the surface resistor is reduced.